So moving on to the rest of the problems, we want to find the derivative of the inverse of this function restricted to where x is, oops, I think I said in one place 5 over 2 when it should have been -1/2. I'm not sure how that mistake got made, but these should be -1/2 in my solution. Right, how do we find the inverse of a polynomial? Well, one way is to, of course you do that high school method of swapping the x's and the y's and then solving for y. But how do you solve for y? Well, you could use the quadratic equation, in fact, that actually still applies, or you could sort of complete the square, which is really where the quadratic formula comes from. But anyway, I'll just use the quadratic and say that the solutions for y, right, because we're trying to get y in terms of x, the solutions for y are -b plus minus square root b squared minus 4 times a times c. After subtracting x to the other side, c would be equal to this, and then we just sort of distribute and simplify the stuff inside of the square root. Now, since we are restricting to the large values, I'll say, the large values of x, then we would want to pick the, that means picking the large values of y, and if we want y to be the large values, then we would pick the positive square root in this instance. So we pick the positive square root, that's the point. And once we know that the inverse function is this with the positive square root, then finding the derivative, that should be easy. I shouldn't have to tell you by now how to do that. So, and in fact, you can calculate it and check your answer in SimPy. So, now, if we restricted to the low values of y, right, low values of x, if we restricted the domain of the original function to the very negative values of x, then that would be restricting y in the inverse function, meaning that we pick the negative square root. Finally, here is my reproof of the trig derivative formulae using Euler's identity, my favorite. So, taking the derivative on both sides, on the left-hand side, I just use chain rule with ix as the inner function. Now, on the right-hand side, we are pretending that we don't know what the derivative of cosine is. So we just leave it as the derivative of cosine and try to solve for it, and likewise for sine. Now, how do we actually do that? Well, for one thing, we know that this is a real function, and this is a complex function, right? Because it's got the I on it. So when I take this and distribute it out and split it into real and imaginary parts, then I can group them accordingly. So if I multiply this out, right, I know that I can replace e to the ix after the derivative with cosine x plus I sine x. I distribute the I. Importantly, I times I is -1, so I get a real part here. And then I rewrite it so that the grouping becomes obvious. The real part, having taken the derivative, is equal to the cosine derivative, and it's negative sine. The imaginary part is the derivative of sine. And there you have it. That's a proof that the derivative of sine x is equal to cosine x, and the derivative of cosine x is equal to negative sine x.